Okay, we're we're back to chapter 16.6 now, uniform circular motion, simple harmonic motion. There's a relationship between the two. And this is actually where we get the mathematics of simple harmonic motion. So uniform circular motion, of course, is just like a ball going around and around in a circle at a constant speed around the edge of the circle, a rotating disc. And in this case, what we're going to do is we're going to put this rotating disc kind of like on a wall with some lights shining down, and we're going to look at the shadow of this ball that's traveling around the edge of this disc on the floor. And what we'll see is we'll see this ball moving back and forth on the floor, the shadow moving back and forth on the floor as the ball goes around and around on the disc. And the movement of the ball on the floor will actually follow the same movement as a simple harmonic oscillator, to follow the model of a cosine or a sine curve along the floor. And so there's an analogy here between the two movements, the circular movement and the simple harmonic motion movement. And if we go ahead and we do the math here, we know that we have some angle theta, and that the distance that we are along the circle, if we figure out how far it is in the x direction, we're using the cosine of theta. If we figure out how far it is in the y direction, we use the sine of theta. We know that we can use Pythagorean's theorem to figure out the y distance as well. So we've got all kinds of things that we can use here, and in the end, what we end up with is the same thing that we had before, which is that the position that it is in the x direction is equal to the maximum distance it can go in the x direction times the cosine of theta, where theta is equal to omega times time, because that's just a definition of omega. Omega is theta divided by time. Solve that and you get theta equals omega times time. And then of course we also know from previously that it's equal to 2 pi over the period times the time. And so then we can say that our omega is equal to 2 pi over the period. So there's a good equation to keep your mind on there, to remember. Highlight that for you. So omega equals 2 pi divided by the period. Really important equation. And then omega, we're going to give a name. We're going to call it the angular frequency. It's also the angular velocity, or the rotational velocity of the ball going around this circle. But you can see here, as we map out the position of the ball in x, it does follow that sine or that cosine curve, however you want to think about it. This is a cosine curve in this case. And then the velocity also can be mapped out, and we will end up with an equation for the maximum velocity, just like we had before. We'll have an equation for the period, equation for the velocity if it's a spring, an equation for the period if it is a, just all kinds. This is the equation for the period if it's on a spring. We get all the same equations that we did before, but we get them from doing circular motion. So what we really learned there is that a circular motion object undergoing a constant circular motion, or motion of uniform circular motion, where the speed around the edge of the circle is constant, is a harmonic oscillator. Now, in real life, our harmonic oscillators are not frictionless, and they're not perfect springs, and they're not perfect pendulums. And because of that, what usually happens with them is they usually get perturbed in some way. They usually get the oscillation gets changed over time. And the most common one is probably the damped oscillator, where you start off with a big oscillation, a big vibration, then it gets smaller and smaller and smaller because of something that's taking energy out of the system, usually something like friction. And so if we put this in the work energy theorem, we have a non-conservative work, which would be friction. And the friction is equal to a change in kinetic energy and potential energy. It slows down the oscillator, so that changes the kinetic energy, but it also doesn't allow the oscillator to compress a spring or go as high as it was if it was a pendulum before, so it also changes the potential energy of the oscillator. And there are a couple of different ways that you can damp an oscillator. You can have a system that is overdamped, which would be A here. Curve A here represents an overdamped oscillator, where an oscillator is damped before it even gets through one complete cycle. And then you have an underdamped, which is Actually, I'm sorry, A is actually what they call critical damping. This one is actually your underdamped one. Just has a very small amount of damping, so it slowly decreases over time and eventually goes away. Critical damping allows it to go through one oscillation and then it dies off. And then this one here, which is curve B, they call an overdamped. This one's critically damped. This one's overdamped. It damps it before it even goes. Before it even goes through a cycle. But anyway, I don't know why they're showing that curve. That curve's not very representative of what we're trying to understand there, but it's kind of a goofy curve. But anyway, they should combine the two curves so you can see the waves underneath them as well. But the point being is that we have different types of damping, and that's fine. So here we have, we're going to introduce friction into this system, I would assume. See, yeah, there is a simple friction between the object and the surface. Coefficient of friction they give to us, and we want to know how long this thing is going to travel with the friction involved, because the friction is going to just constantly take energy out of the system. So what you do is you calculate the total amount of energy in the system to begin with, which is, if you compress the spring or stretch the spring and just hold it there, all of the energy is in the spring, and that's going to be potential energy. And then you're going to set all of that energy equal to the amount of work needed to be done by the friction to damp it all out. And so it's the force of friction times the distance, and then you can calculate the distance, and that's exactly what they're going to do here. So here's their work, force times distance here, and they let that force times distance equal the potential energy of the springs at the start, and then they calculate they solve it for the distance, and then they plug in their numbers, and they know how far it's traveled total. And that's just a distance, it's not a displacement. So the spring, may be going back 2 or 3 centimeters at a time, but in a total it travels 1.59 meters of distance as it goes back and forth, back and forth, back and forth, and gets damped and slowly oscillates its way out of oscillation, runs out of back and forth room. Then the other side of the world is the forced oscillations, where we cause things to vibrate more and more and more. And that is by adding force into the system. So or adding energy into the system instead of taking energy out. Same thing adds energy as we're subtracting energy, some kind of force. And when the force is applied is really quite important. For example, if you hold a ball on a rubber band here, and you move the rubber band up and down very slowly, and the ball up and down very slowly with your finger, just barely moving it up and down and up and down, then what you're going to get is you're just going to get the ball moving up and down without anything really going on. However, if you move it really, really fast, the ball will just move very fast, but it won't move a lot. So in either of these cases, moving it slow or moving it fast, the ball doesn't move that much. However, somewhere in between, there's this place where if you move it up and down, the rubber band will start to stretch and contract and stretch and contract at just the right rate with your finger. We call this the resonant frequency, where the ball starts to really bounce out of control, where it gets really, really bouncy. And everybody knows this. If you play the game with the paddle and the ball on the rubber band, or if you any kind of thing that requires an oscillation like that, if you find just the right frequency, you can get it to really bounce really well, and bounce a lot. We call that frequency resonance, and every system has a resonant frequency, and some have more than one resonance frequency. This resonant frequency we call F naught, F or F sub 0, and that is, there are other ones that we would maybe call F sub 1, F sub 2, F sub 3, so on and so forth. But that resonant frequency is often something that we're looking for in physics, or something we're trying to avoid in physics. Sometimes we want things to resonate, sometimes we don't want them to resonate. For example, in musical instruments, we want certain notes to resonate in the instrument so that they sound louder and they sound better. But in building bridges, we don't want vibrations to resonate, because resonating vibrations in building a bridge could actually cause the bridge to break, and have done in the past. And I'll show you an example of that. So in Washington, there was a bridge called Galloping Gertie, and it was called this because of the resonances. So it was just a normal suspension bridge, and the problem with this normal suspension bridge is that it had a resonant frequency that was easily excited by the wind across this little place where the bridge was built. And so over the years, after the bridge was built, actually it was just a few weeks after the bridge was built, and this was built in the 40s. Just a few weeks after this bridge was built, you could see a resonant frequency. It was actually waving, and it was waving a lot, actually. This was months after it was built, maybe even a year. But it became so bad, you can see here, that it was dangerous to be on. And so they closed the bridge, didn't allow any traffic on it. Eventually, it got so bad. Let's see if we can. Goodness, this video is giving me trouble. Eventually, it got so bad that it collapsed. And here you can see the bridge from another angle. There's a person walking on the bridge right here. But then eventually the road on the bridge starts to break apart. The concrete starts to break. You can see little cracks growing in it there. But then eventually let's see here. And there was a professor that went out on the bridge to do something. I don't know what. He ended up leaving his car out there. It was so dangerous. I think he was trying to demonstrate that he could drive if he drove right along the middle, because see, the middle of the bridge is not moving very much. But the edges of the bridge are moving so much that, your car would totally slide around. But eventually the bridge did totally collapse. It broke the elastic limit of the materials, and the steel and the concrete all just shattered and broke apart, and that bridge was no more. And when they rebuilt this bridge, they were very careful to make a very specific study of the winds in this area and the span across this area, so that they didn't build another bridge that would easily resonate with those winds, that would easily start to vibrate with those winds. They had to build it in a very specific way so that it wouldn't resonate. And everything has kind of a resonant frequencies. Even humans have resonant frequencies of different kinds. And sometimes resonant frequencies are good, sometimes resonance frequencies are not so good. This is an example of not so good resonant frequency. So let's see if I can get back to my book here. Here's my book. Okay, so come on. I want this to work here. Why is it not working? Worky. There we go. Okay, let's see here. So, here they show a chart of what it looks like to pass through the resonant frequency. If you have a lot of damping, of course, it won't increase the amplitude. This curve represents the amount of oscillation. So, if you go up here, it's a big oscillation. It's a big vibration. And if you have a lot of damping, it won't be very big. And if you have a medium damping, it will get quite big, almost 3 times as big as with damping. But if you have small damping, then you get a very tight peak here where it just wants to oscillate just at this resonant frequency right in the middle, and just sits there. and it'll be really big frequency. And that can happen with a lot of things. Here they show a picture of the bridge. They also talk about the resonant frequencies in a glass. For example, if you have a goblet, it's a fairly high note for a drinking goblet, but you can sing a high note, very, very high intensity, and break a glass. And it's been done. It's been done on many occasions. And it's just a matter of finding the frequency of sound that will make the glass vibrate more and more and more and more until it breaks. That's what we call resonance. We're going to come back to resonance in the next chapter, and we're going to move on now to waves. So waves, of course, are the propagation or the movement of these vibrations caused by oscillators from one place to another. And they carry the energy from one place to another. And they can move through materials, but they can also move through space without any materials. We'll first talk about waves that move through materials, for example, water waves. So a water wave is caused by an oscillation. Usually it's caused because gravity is pulling from the moon and the gravity from the sun are pulling on the earth. Well, the water can move. And so when the water gets pulled on that's on top of the earth, it moves, it sloshes around, and then it sloshes back, and then it sloshes around. And gravity can only pull it so far, and then it kind of lets it go, and then it sloshes back and forth. And so you always have these waves going on anytime you're near a body of water that's big enough to get pulled on. Essentially, you're going to have this sloshing. And of course, wind can cause waves, so it's another force that can cause an oscillation or a disturbance in the water. And boats can cause waves, and people jumping in the water can cause waves. All kinds of things can cause waves. Any kind of force that causes a disturbance and an oscillation in the water of some kind will create a wave that will move outward from that, and those are water waves. Water waves are what we call transverse waves. In other words, the transverse means across the movement. So the wave is moving one direction. It might be moving from left to right here, for example. But the waviness of it, the water is actually moving up and down. So there's energy that's being carried forward, but the water itself is actually just moving up and down. And the water can be moving forward as well, but it's mostly the wave. It's mostly just pure energy that's moving forward. Pure energy is a bad way to say it, but it is. I mean, for example, a duck can sit here on the water, and as the wave goes by, the duck will mostly just go up and down. They'll get moved forward a little bit by the friction under them and everything else, but it's mostly just kind of up and down. And again, we have a lot of the same kinds of things that we've used for previous stuff. We have, for example, frequencies and periods of the wave, but we also have a wavelength, because this is now a physical wave that has length to it. If you go from the peak of a wave to the peak of the wave, and you measure that distance, it's what we call a wavelength, or lambda. You can also measure from the trough to the trough of the wave. But that's what we call a wavelength, and so now we have a wavelength and a period. And if you take the wavelength over a period, it's a distance over a time, and it becomes a velocity. And we call that the wave velocity, or VW, is equal to wavelength over time. Or you can also use frequency times wavelength to get the wave velocity. Or it's often called the wave speed as well. And that is essentially the speed at which the energy or the information or the oscillation is traveling. You have this oscillation or this disturbance that's traveling through the water, and the speed that disturbance moves through the water is the velocity of the wave, or the wave speed. So here we have an example where we have a wave crest that has a 10-meter distance between wave crests, and the time that it takes a seagull to bob up and down is taking 5 seconds, so that's our period. And we have a wavelength and a period. We can divide the wavelength by the period to get a wave velocity, and it ends up being 2 meters per second, 10 divided by 5. So transverse wave, the wave goes up and down, but the wave is waving up and down, but it's moving forward. There's another kind of wave which we call a longitudinal wave, or a compression wave, where if you take a slinky like this and you squeeze the springs together and then you release the springs, you'll see a compression wave. You'll see some compressed spring moving down the slinky, and this is what we call a compression wave, or a pressure wave, or a longitudinal wave. Longitudinal meaning along the wave, or along the path of the wave. So the wave is moving in one direction, but also the waviness is moving in the same direction. It's just compressing and expanding along the direction that it's moving. So that's a longitudinal wave. sound waves are longitudinal waves, and certain parts of earthquake waves are longitudinal waves, and other things like that. There are many things that are compression waves. So here is an example of some waves here. We have somebody playing a guitar, they strum the strings on the guitar, and there are some devices there that turn that wave into an electrical wave in the wire, and then you can amplify it and turn it into a sound wave by moving the cones in the speaker, and the sound wave can come out here, and I can actually hear it with your ear as the sound waves hit your eardrum, and it sends a signal to your brain to say there's sound there. And then you could also make some kind of a device, like a piece of paper, that would be wiggled by the sound wave, and it can actually be done. The next interesting thing about waves is that you can add them together, and we add them together in what we call superposition. Essentially, you just kind of lay them on top of each other and see what happens. So if you have two waves like this, that when you lay them on top of each other, the same exact wave, it's just like adding. You add this height to this height and you get double the height. And then where the waves are zero, you get zero. When you add this little height in the negative direction, this little negative height, you get a big negative height. And this is what we call constructive interference, where the waves build each other up to make a bigger wave. And this would be like having two speakers instead of one. Two speakers will give you more sound, so you get more amplitude is more sound. But the wavelength is still the same. It hasn't really changed. It hasn't changed how long the wave is. It hasn't changed the distance between the peaks. It's just changed the height of it. That's what we call constructive interference for a very simple single frequency wave. However, you can also get waves that are not, they're out of sync, or they're what we call out of phase. So these particular waves are 180 degrees out of phase, so that when this one is at its peak, this one is at its trough. When this bottom one's at the peak, the top one's at the trough. And so when you add these up, they all actually cancel each other out, and you get a resultant wave of zero. And that can happen in speakers as well. If you have two speakers and they're facing each other, and you wire them up so that one of them is wired correctly and one of them was wired opposite of correct, then they will be out of phase. And as you point them towards each other, right in the middle between the two speakers, you will have a dead zone where it doesn't sound like there's any sound in the middle. And that's not a great thing for speakers, because you want speakers to make sound, but it is a pretty cool demo. And then finally, superposition can work with waves that have different frequencies as well. So example, wave 1 has this really long wavelength, wave 2 has these really short wavelength and this really high frequency. If you add them together, you just get a little bit less of this wave 1, because this one's just a little bit negative, and then you add it together, you get a little bit less. And then if you add together this really big tall thing with this thing, you get a little bit more, because this one's positive and this one's positive. So you get a little bit more, and so on and so forth. You just add them up, and that's your resultant wave if you do add those two up. Come on now, there we go. Okay. So, you can have waves that add up like that, but you can also have standing waves that can add to themselves. And what a standing wave is a wave that is created that on a, let's say it's on a string, but we tie the string to the wall. So that I make a wave that goes down the string and it hits the string at the wall, and then it bounces off the wall and comes back. And then as they bounce back, if they add to each other, if the wave going down and the wave bouncing back are in phase with each other and lined up so that their peaks are with the peaks and the troughs are with the troughs, we can get what we call a standing wave. And they will build up and you'll get a resonant standing wave. But you can also cancel them out. And you can also get standing waves that are in between resonant and zero, for sure. So when we start doing waves like this, then we learn that when you have two ends that cannot move, the longest wavelength that you can make is equal to twice this distance, because you can make a string go up and down like this inside of a little cavity like this, where it goes up and down in the middle. We've all probably seen this in different situations in our lives, where you can make a wave that goes up and down in the middle, but of course the ends are tied down so they can't move. And what this really means is that your wavelength, since you have to go all the way along a complete wave, is all the way from this left-hand side all the way over to this area over here that's not even in the experiment. It's not even there. Why does it have to go a little further? Because that's a complete wave. So if you have a cavity that is L in length, and you want to know what its wavelength is, if you've got it at the lowest possible resonance, you've created this standing wave, then you know it's going to be about twice the length of the cavity that you've got there. Of course, it won't be perfect because you're probably not using physics string. But that's okay. But there's also situations where you can create two bumps in your wave. And in this case, you've created a resonant wave where you have a complete wavelength inside. And you can also do one with three, where you've got 1.5 wavelengths inside of the same space. And it's just a matter of shaking the string faster. Go a little bit faster, you can make 2 loops. A little bit faster, you make 3 loops. And we can actually calculate those frequencies that do those things for particular lengths and for particular types of string. And that's kind of where we're going to go at next here. So, excuse me. Actually, one more thing to cover here is what we call beat frequencies. If we have two waves that are not the same frequency and we add them together, sometimes if they're very close in frequency, we hear this effect that goes wah, 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 wah. And that's what we call beating. It gets a little bit louder and a little bit softer, a little bit louder and a little softer. And the reason for that is because at certain places the frequencies are pretty well lined up, so they constructively interfere, like places like here and over here where the wave is pretty big for the resultant wave. And then there are places where the constructive of one and the destructive of the other, or sorry, not essentially. What happens is you get some places where the peaks and troughs line up and you get destructive interference, so that it gets really, really quiet, and other places where it gets really, really loud from that constructive interference. So you get this frequency of a loud, soft, loud, soft, loud, soft, which we call a beat frequency. And the beat frequency is actually fairly simple. It's just the difference between the two frequencies. So it's right here. You take the difference between the two frequencies, take the absolute value, because we're only going to use positive numbers, and that's what we call the beat frequency between two sources. Okay, so now wave intensity. We know that the work to create a wave is going to be kx squared, where the k is the spring constant of a spring, if that's what caused the wave, so it's kind of related. But we know that intensity is power divided by area. We've learned about that before. And we did this problem before where we calculated the intensity of sunlight on the Earth, so we won't go through that again. We've done this problem before. However, we haven't done a problem like this. We have the combined intensity of two waves. So we're going to have constructive interference, where we have two waves that we're going to add together and make a final wave. So we have two identical waves, each with 1 watt per meter squared intensity, and they're going to interfere constructively, and we want to know the intensity of the resulting wave. So intensity is proportional to amplitude, it turns out, amplitude squared. And the new amplitude, let's see here. Yeah, we want to know the new amplitude so we can calculate the new intensity. So anyway, we know that it's proportional to the amplitude squared, but we're going to have an amplitude of 2x, so that's going to be 2x squared, which would be 4x squared if we do that. So what's really going to happen is that we have a ratio of new intensity to old intensity of equal to 4 from our 4x. Let's see, it's intensity over intensity, right? Yeah. So intensity over intensity is going to be equal to 4 because everything else is going to cancel out. So we just calculate what are we going to need for our I, and it's going to end up being 4 watts per meter squared in the end when we solve for that. I equals 4I and so on and so forth. And that just about covers it. We're done with chapter 17. We have chapter 18 to do. And I will come back with a homework video hopefully later today, maybe tomorrow.